Testing, can you hear me? Okay, my video is public now, so I'm going to be studying calculus. So last time I studied about divergence and curl. I did some research about it and I think I understood curl a little bit better. This stream, I'll study surface integrals. All right. We have seen that the line integral is an integral over a path in a plane or in space. However, if we wish to integrate over a surface rather than a path in space, then we need a new kind of integral that can handle integration over objects in higher dimensions. We can extend the concept of a line integral to a surface integral to allow us to perform this integration. Surface integrals are important for the same reasons that line integrals are important. They have many applications to engineering and physics, and they allow us to develop higher dimensional versions of the fundamental theorem of calculus. Surface integral is similar to a line integral, except the integration is done over a surface rather than a path. Didn't we do this before with double integrals? Maybe I'm getting confused. In this sense, surface integrals expand on our study of line integrals. Just as with line integrals, there are two kinds of surface integral: a surface integral of a scalar valued function and a surface integral of a vector valued function of a vector field. Before we can integrate over a surface, we need to consider the surface itself. Recall that to calculate a scalar or a vector line integral over a curve C, we first need to parameterize C. In a similar way, to calculate a surface integral over surface S, we need to parameterize S. That is, we need a working concept of a parameterized surface. In the same way that we already have a concept of a parameterized curve. Parameterized surface is given by a description of the form RUV, XUV, YUV, and CUV. Notice that this parameterization involves two parameters u and v because a surface is two-dimensional, and therefore two variables are needed to trace out the surface. Parameters u and v vary over a region called the parameter domain or parameter space. The set of points in the UV plane that can be substituted into R. Each choice of u and v in the parameter domain gives a point on the surface, just as each choice of parameter t gives a point on a parameterized curve. The entire surface is created by making all possible choices of u and v over the parameter domain. Describe surface as parameterized by uv. U goes from minus infinity to infinity, v goes from minus infinity to infinity. Let me see. Cos u, sin u, x. So this is cos u. Can I draw it over here? U, v. Hold on. All right. cos u, cos u, sin u, cos u. So x will follow a cos function, y will follow a sine function. If you think about it, what I'm thinking is in a 3D graph, let's call this C, X, Y. If x is cos u, so as u goes from minus infinity to infinity, what I'm saying is the shadow on u should follow a sine curve, right? Sorry, I mean cos curve. So something like this. Yeah, this x goes cos curve. This is the xy plane. No, I'm getting this wrong. Cos u goes from infinity to negative infinity to infinity. And u is 0, 0, 0. Yeah, let's see, cos u, sine u, and then v. So this is a cylinder. To get an idea of the shape of the surface, we first plot some points. Since the parameter domain is all of R square, we can choose any value of u and v and plot the corresponding point. If u b is 0, then R00 is 100. So point 100 is on S. Similarly, points pi 2 is equal to minus 102 and R pi over 4 is equal pi over 4 is equal to 014 are on S. Although plotting points may give us some idea of the shape of the surface, we usually need quite a few points to see the shape. Since it is time consuming to plot dozens or even hundreds of points, use another strategy. To visualize S, we visualize two families of curves that lie on S. In the first family of curves, we hold U constant. In the second family of curves, we hold V constant. This allows us to build a skeleton. First, suppose U is a constant K. The curve traced out by the parameterization cos k sin k, which gives us a vertical line and goes through point cos k sin k in V on the xy plane. So on the xy plane, there are vertical lines, keeping sin k and cos k constant and changing V from minus infinity to infinity, we get these vertical lines for different constants of sine and cos. Now, suppose that V is a constant k, then the curve traced out by the parameterization is sin u, cos u sin u k. Also, for different constants of k, we get this, right? So putting them together, we get this. Right. It follows from example 6.58 that we can parameterize all cylinders in the form x square plus y square is equal to r square is If S is a cylinder given by the equation S square plus Y square is equal to R square, then the parameterization of S is R U V, R cos U, R sin U, and V. All right. We can also find different types of surfaces given their parameterization, or we can find a parameterization when we are given a surface. Describe surface S parameterized by U cos V, U sin V, and then U square. Let me think about this. If V is constant, if V is constant, actually keeping U as 1, if U is 1, then Z is U square, which is 1, and then we have a circle, right? We have a circle at, that looks ugly. Or should I draw this? Like that. We have a circle here when U is 1. U is 1, 1, 1, cos V, sin V, and 0 to 2 pi. Okay, this goes from 0 to infinity. So if U is a little smaller, cos V and sin V is like scaled down, right? And then U square, this follows a parabola, right? Oh, I see. So it's like a parabolic. It's like a, it's like, it's a parabola, but like rotated 360 degrees. That's my guess. Yeah. Given a parameterization of the cone x square plus y square is c square lying up on or above the plane c is equal to -2. So we have to find a parameterization. Example, this was 6.59. This is 6.60. X square plus y square is equal to z square. Let's say z is equal to t. Then we have x square plus y square is equal to t square. But that doesn't help, right? V now x square is equal to y square is equal to v square minus x square. Okay, let's say x is equal to u. U square. So then we have RUV u square v square minus u square and then v square. Point on the cone at height u has coordinates u cos v, u sin v, u for angle v. Hence, a parameterization of the cone is RUV, U cos V, U sin V, U. Since we are not interested in the entire cone, only partitions on or above plane C is equal to -2. The parameter domain is given by -2U to infinity and 0V to 2 pi. What was wrong with my curve? What u square? Okay, let's try u square v square. U square v square u square minus e square. What is this? So why doesn't this work? X square plus y square uh square root. Okay. Yeah, we discussed parameterization of various surfaces, but two important types of surfaces need a separate discussions. Spheres and graphs of two variable functions. To parameterize a sphere, it is easy to use spherical coordinates. Sphere or radius 4 centered at the origin is given by the parameterization r phi theta rho cos theta sine phi, rho sine theta sine phi, and rho cos theta, cos phi, I mean. The idea of this parameterization is that as phi sweeps downwards from positive z-axis, a circle of radius rho sine phi is traced out by letting theta run from 0 to 2 pi. To see this, let phi be fixed. Then you have this. Finally, need to parameterize the graph of a two-variable function. We first let z is equal to f(x,y). Be a function of two variables. The simplest parameterization of the graph of f is rxy, xy, fxy, where xy vary over the domain of f. For example, the graph fxy, x square y can be parameterized like this, where the parameters x and y vary over the domain of f. We only care about a piece of the graph of f, say the piece of the graph over rectangle 1, 3, 2, 5. We can restrict parameter domain to give this piece of the surface. Hold on a minute. Uh, sorry, something just came up. All right. Similarly, also I will have to go in a while, so I don't know how long I can do this. Similarly, if S is surface given by the equation x is equal to gyz, or equation y is equal to hxz, then a parameterization of S is ryz or rxz respectively. For example, the graph of the paraboloid 2y is equal to x square plus c square can be parameterized by rxc. Notice that we do not need to vary over the entire domain of f because x and c are squared. Let's now generalize these notions of smoothness and regularity to the parametric surface. We call that a curve parameterization. RT is less than or equal to T, which is less than or equal to B, is regular if RT is not equal to 0. The derivative is not equal to 0 for all T. That doesn't make any sense. It's regular if the derivative is not 0. For a curve, this condition ensures the image of R is really a curve and not just a point. I mean, what if it's like a hill if the derivative is 0 at one point? For example, consider the curve parameterization Rt is 1, 2. The image of this parameterization is simply a point 1, 2. Which is not a curve. What do they mean by the image? I can't remember. Notice that also the derivative is 0. The fact that the derivative is the 0 there indicates that we are not actually looking at a curve. But what if it's a hill though at one particular t? Let me think. Okay, what if it's a straight line? What then? What if there's a curve and like a small interval of t, it's a straight line. Then it goes back to being a curve. Then what? And analogously, we would like a notion of regularity for surfaces that so that a surface parameterization really does trace out a surface. To motivate the definition of a regularity of a surface parameterization, consider parameterization RUV is equal to 0 cos V 1 0 U1 0 V pi. What's the point of view? Although this parameterization appears to be parameterization of a surface, notice that the image is actually a line. How could we avoid parameterization such as this parameterization that do not give an actual surface? Notice that RU is 0, 0, 0 and RV is 0 minus sign V and 0. The corresponding cross product is 0. The analog of this condition is derivative of R is equal to 0 is that the cross product is not 0 for any point UV in the parameter domain, which is a regular parameterization. So regular parameterization of the cross product of the derivatives is not hold on. Is not 0 for any point UV in the parameter curve. Why any point? If it was like in the entire domain, I would get that for any point. If parameterization R is regular, then the image of R is a two-dimensional object as a surface should be. Throughout this chapter, parameterization RUV, XUV, YUV, ZUV are assumed to be regular. Recall that the curve parameterization from for T between A and B is smooth if the derivative is continuous and the derivative is not 0 for all T. Uniformly, a curve parameterization is smooth if the resulting curve has no sharp corners. Definition of a smooth surface parameterization is similar. Informally, a surface parameterization is smooth if the resulting surface has no sharp corners. Surface parameterization RUV is smooth if vectors this and this is not 0 for any choice UV in the parameter domain. A surface may also be piecewise smooth if it has smooth faces but also has locations where the directional derivatives do not exist. So this is smooth, this is piecewise smooth. In the pyramid, sharpness of the corners ensures that the directional derivatives do not exist at those locations. Our goal is to define a surface integral, and as a first step, we have examined how to parameterize a surface. Second step is to define the surface area of the parametric surface. The notation needed to develop this definition is used throughout the rest of this chapter. Let S be a surface with parameterization RUV over some parameter domain D. We assume here and throughout the surface parameterization is continuously differentiable. Assume for the sake of simplicity that D is a rectangle. Divide rectangle D into subrectangles Dij with horizontal width delta U and vertical length delta V. Suppose that I ranges from 1 to M and J ranges from 1 to N so that D is subdivided into M in rectangles. This division of D into subrectangles gives the corresponding division of S into pieces Sij. Choose point Pij in each piece Sij. Okay, so within the UV domain, we divide it into squares, and for each square, we have this area over here. Now that we can form a grid with lines that are parallel to the U axis and the V axis in the UV plane. These grid lines correspond to a set of grid curves on surface S that is parameterized by RUV. Without loss of generality, we assume that Pij is located at the corner of the two grid curves, as in figure 6.65. If we think of R as a mapping from the UV plane to R cube, grid curves are the image of the grid lines under R. To be precise, consider the grid line that go through point UI, Vj. One line is given by X, UI, and Y is equal to V. The other is given by U is equal to X, Y is equal to Vj. In the first grid line, the horizontal component is held constant, yielding a vertical line through UI, Vj. In the second grid line, the vertical component is held constant, yielding a horizontal line, UIVJ. Corresponding grid curves are RUIV and RUVJ. These curves intersect at point Pij. Okay, wait. Consider grid lines that go through point UIVI. So you're considering this grid line going through UI. So that's first grid line. Wait. Horizontal component is okay. Think for UIVJ. One grid line, we have one grid line defined UI and all V values. Then this grid line defined for Vj and then all the U values. And then we have the corresponding RUIV and the corresponding RUVJ. Corresponding RUVJ for this point where it intersects the curve Pij. Now consider the vectors that are tangent to these grid curves. For grid curve RUIV, the tangent vector at Pij is tangent vector. Okay, it's RV. Okay. For grid curve RUVJ, the tangent vector at Pij is, okay, now it's with respect to U. If vector n, which is the cross product of these, exists and is not zero, then the tangent plane at Pi exists. If piece Sij is small, then the tangent plane at point Pij is a good approximation of piece Sij. Okay, so I get they're finding a normal vector, which is the cross product. Small enough, then the tangent plane at point Pij is a good approximation of piece Sij. Okay. So if there's a tangent plane cutting through this, which has the same derivative as TV and TU, then it's a good approximation for values very close to Sij. Tangent plane at Pij contains vectors TU and TV. Contains vectors TU. What is this? TU multiplied by Pij? Therefore, the parallelogram spanned by TU times Pij and TV times Pij. What are they doing, Pij? Is in the tangent plane. Why do they have these brackets? Shouldn't it be just T? Oh, wait. This is a function. So the derivative with respect to U at point Pij. Yeah. Since the original rectangle in the UV plane corresponding to Sij has width delta U and length delta V, the parallelogram that we used to approximate Sij is the parallelogram spanned by delta U TU and delta V TV. In other words, we scale the tangent vectors by constant delta U and delta V to match the scale of the original division of the rectangles in the plane parameter domain. Therefore, the area of the parallelogram used to approximate the area of Sij is this. Delta V TU times delta, okay, delta U TU times delta V TV, cross product of these, and we take U and V out. Varying point Pij over all pieces Sij and the previous approximation leads the following definition of the surface. Following definition of the surface area of the parametric surface. One thing I don't understand, TU is not a tangent. TU is not a unit vector, right? It's tangent but not unit. But the thing is, delta U TU won't be the same length as the Sij component, right? So this here won't be the same length as this, right? So is it really a good approximation for the area of this? I don't understand why these two make a good approximation for the area of this. Let RUV, XUV, YUV, ZUV with parameter domain D be a smooth parameterization of surface S. Furthermore, assume that S is traced out only once as UV varies over D. Surface area of S is du cross product dv dA. Calculate the lateral surface area of the right circular cone with height h and radius r. Right circular cone with height h and radius r. So they defined it using kv cos u, kv sin u, and then v. The idea behind this parameterization is that for a fixed v value, the circle swiped out by letting u vary is a circle at height v and radius kv. As v increases, the parameterization sweeps out a stack of circles, resulting in the desired cone. With the parameterization in hand, we can calculate the surface area of the cone using equation 6.18. Tangent vectors are tu and tv. Therefore, they said they want height h, right? Tu and tv. Equation 6.18. But why are they doing 0 to 1? That I don't understand. 0 to 1. Magnitude of this vector is, you get this. By equation 6.18, the surface area of the cone is, wait, I still don't understand why it's 0 to 1. U varies from 0 to 2 pi. Then V varies from 0 to h. Oh, the derivative. Yes, yes. If we derivative each side, with respect to u, we get 0, and with respect to v, we get 1. Yes, yes, yes. That's, I got confused. The derivative with respect to u, derivative with respect to v. Hold on, I may be busy. Let me check one thing. Okay, I think I have to go, but I will continue this thing next stream. So anyways, I will see you guys next time.